Hey guys, I decided to start streaming, because I thought it might be fun to stream some Calc 2 homework specifically. Right now we are on chapter 11.1 of, I think the book title is the Stewart, uh, Fundamentals, something something. Uh, See, I just got a new computer, so I'm kind of, a little bit of it is getting the hang of it, a little bit of it is just, I'm enjoying it. I like it. So let's see, James Stewart calculus textbook, early transcendentals. So we are on 11.1, which is all about sequences. So I'm just going to be doing some of the homework, and this should save as a FOD in case anyone needs to come back here. So 11.1, sequences. What are sequences? Before we start the chapter, there's two ways of defining a sequence. You can either think of it as a list of numbers, so like uh, 1, 2, 3, 4, 5, right? That is a sequence. Usually sequences can continue. They're generally expressed as a sub n. So 1 could be a sub 1, 2 is a sub 2, 3 is a sub 3, right? With the n subscript referring to which number in the sequence it is, right? Something special about sequences is that they can only be, so you can define a sequence as a function, right? So similar to say how f of x could be expressed as, you know, x plus 1. Well, a sub n could also be expressed as like n plus 1. But um, for sequences, they are defined, their inputs, how do I put this? Um, their inputs are only the set of all positive integers, right? So like 1, 2, 3, 4, 5, and so on and so forth, right? 101, 256, all those. So the big question that arises with sequences, the one that we usually try to answer is, does it converge or diverge? Where converging just means as n approaches infinity, does the sequence approach a finite number? Now you might be thinking, well, how would something going along to infinity, so if you were to graph a function, right? Say, f of x equals x, and something similar for um, a sub n equals n. So it's like an f of x equals x function, but only at 1, 2, 3, right? And these negative numbers wouldn't be defined. So it goes on like that. How can this approach a finite number? You would think, oh, it's much more common for it to do what's called diverging. This one makes more sense. So as n approaches infinity, um, sequence diverges, which means that it just approaches infinity, or it doesn't exist, or it approaches a negative number, or for the case of like, a sine function, it'll just oscillate, right? It's basically everything that's not just approaching one number. So diverging seems a lot more possible, right? You could think of a bunch of situations, a bunch of functions where it'll just go towards infinity or a negative infinity, or it approaches whatever. But converging, right? A good example would be 1 over x, or in the case of a sub n, 1 over n. So I'm just going to grab f of x equals 1 over x first, right? Because I think that's a little bit easier to graph because I don't have to do points. I could just, graph with a continuous line. So as you go to the right, what you'll see is that, at x equals 1, it's just 1 over 1. At x equals 2, it's 1/2. At 3, at 4, it's 1/3, 1/4. And you can kind of see that there's going to be a little bit of a trend. This whole function, 1 over x. So as x approaches infinity, so as it goes along to the right, this whole function is gonna approach 0, right? It'll never reach there, but we can say that the limit, which is just the number that it's approaching, is gonna be 0. So that's just one case of how a sequence can converge. And right, this is for a function, but it's very similar, right? Since a sequence is just the set of all positive integers, well, f of x is the set of all real numbers, right? It's continuous from negative infinity to infinity, usually, unless you involve these continuities. So then this set here is inside of this set. So if a property of a function of x, say 1 over x, goes, as, this approaches infinity, as this goes to the right, you could apply the same rules as if it's for a sequence as if it is a function. So that means that um, all the rules we had for limits, particularly limits at infinity, we can just apply to sequences, which is, very convenient. Right? The only hard part is just remembering all of that, all of our little rules for n0. All right, so that's a little bit of the basics of sequences. And I think I'm just going to start on some of the problems that I thought were interesting. Or, start off a little bit easier, but go on into some of the harder ones, just to kind of go over the rules as we go along. So, all right, let's go on to problem number. So for the 11.1 homework, uh, well, let's get into like actual sequence problems, right? They don't start until like 23. So start with 23. So our instructions for all of these questions are simply figure out if the sequence converges or diverges. And if it converges, find the value that it converges to. So this one is a pretty simple one. Um, if you haven't seen this type of problem before, if this is your first time seeing sequences, well, I wouldn't blame you if you didn't know what to do. But this, as we'll see, this is going to be one of the simpler ones. So first of all, to see if it converges, we're just going to take the limit as n approaches infinity, right, of the sequence, 5n squared over n plus n squared. So our first step is going to be just, so just think of these as like the limit as x approaches infinity of 3 plus 5x squared over x plus x squared, right? You don't really have to think too much about like the difference between these, except for like some specific problems which will use what's called the squeeze theorem, right? Where the domain kind of matters. But for now, we could just kind of think of these, applying x rules. So there's like, I want to say at least two ways to solve this one. Um, so we could use either what's called the horizontal asymptote rule. Well, I guess three ways now I'm thinking about it. So first, I'm going to go through all three because one is probably going to pop out to you as something a little bit simpler, um, as opposed to other ones. So the way I would do it, so method one is just use horizontal asymptote rules, right? If you remember from limits um, at infinity, your function is just gonna go ahead and go towards your horizontal asymptote as you go to the right, as you go to the left for most functions. So for this one, well, for 5n squared plus 3 over n squared plus n, the highest degree of the numerator is 2. The highest degree of the denominator is 2. So for that one, the horizontal asymptote is going to be at, I believe the letters may have been like, I don't know, a over b, right? Where a over b, where a and b are the leading coefficients of, I want to say x to the n over x to the m, where or not x, where n equals m, right? And this would continue to xn minus 1, um, right? Plus, whatever constant, whatever constants you have here, but, all that you're looking at is the, the leading coefficient of your highest degree. So for this one, the limit as n approaches infinity of 5n squared plus 3 over 1n squared plus n. And actually I wrote this wrong. Horizontal at a over b, right? The horizontal asymptote is going to be at a over b, where n equals m in the equation. A x to the n over b x to the m, dot 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 dot, right? And then the top is gonna like be like whatever is the like constant x to the n minus 1 plus x to the n minus 2, whatever. So in this case, our horizontal asymptote is just going to be at 5, where it converges. So not too bad, right? Um, a second method that I thought about when I saw this one was, right, and there's probably more methods than the three that I'm thinking of, but for now, right, limit as n approaches infinity of 5n squared plus 3 over n squared plus n. Right. So if you try to apply the limit directly, right, try to apply the limit, you'll get that this equals infinity over infinity, right? Not exactly equals because, infinity over infinity is kind of a wacky, it's an idea less than a number. So you can't really say it equals infinity, right? You can add 1 to infinity and it'd still be infinity. So it's not a number. It doesn't apply numerical. It doesn't get affected by numerical rules. But this is what's called an indeterminate form. And for every indeterminate form, you could just go ahead and apply what's called L'Hopital's rule, right? And indeterminate forms are 0 over 0, infinity over infinity, negative infinity over negative infinity. And you have some other cases such as 0 times infinity, or let's see, there's some other ones, but we'll get to those if we have to later. So what L'Hopital's rule says is that this limit will just equal, applying L'Hopital's rule, the limit as n approaches infinity, right? Keeping the same limit as, and then we could just derive the top and derive the bottom. So the derivative of 5n squared, that's just 10n. Derivative of a constant just is 0, so we just add 0, which goes away. Derivative of n squared is 2n, and derivative of n is just 1. Okay. Oops. 1. Right, but if we apply the limit directly again, we just get infinity over infinity, which, isn't what we want either. But we could just, we have the same conditions as before. We get an indeterminate form if we apply it directly, so we can just use L'Hopital again. Right, so then this equals the limit as n approaches infinity of 10 over 2, right? Just derive the top over the derivative of the bottom, which, limit of anything, as anything approaches anything of a constant, is just going to be that constant, which is just 10 over 2, which is 5. So this converges, just like the last one. Not too shabby. Okay. All right, so that's another way to do it. And I wouldn't really recommend this one unless you're kind of forced to use L'Hopital. Right, I'm gonna say this third method is probably a little bit easier. And even the first method, right? I prefer the first method, but I'm a little biased. That's what I came up with first. So limit as n approaches infinity of 5n squared plus 3 over n squared plus n. So there's a strategy we could use with this one where we just multiply the top and bottom by 1 over n of the highest degree, right? So highest degree here is 2 for coming from the n squared, and we just multiply on top and bottom by 1 over, in this case, n squared, right? If the top was an n cubed, we would do n cubed, 1 over n cubed, right? And then we could just see what goes on. So the limit as n approaches infinity so we just distribute this, right? And, same thing over the same thing, right? These would cancel. This would just be 1. We're just multiplying by 1, which doesn't change the function at all. So that's why we can use this. Uh, that's why we can manipulate the function like this, because in in practical terms, we're not actually changing the value of the function, we're just changing what the function, how the function looks, right? So as long as we aren't actually changing the function, we could do whatever we want to it. So 5n squared divided by n squared, that's just 5. Oop, it's a little wonky. Plus 3 over n squared. And this is over 1 plus 1 over n. Right, and then we could just apply the limit directly. So this one follows our limit as x approaches infinity of x over r, where r is greater than 0. Right, if it's 0, then it's just 1 over x to the 0. X to the 0 is just 1, which is just 1, which is a constant. If it's anything less than, then um, that would be, you could do, sorry, I'm stuttering. You can treat this as x to the negative r, and then, since it's in the denominator, we could bring it up to the numerator. We would just get a limit as x approaches infinity of x to the r, which is infinity. Or something like that, right? It's probably didn't use the best language, like I wouldn't put that in a book or anything, but um, in terms of like trying to think about it, right? You could just see that, oh, if it's, x to the negative 1, you could bring the x to the negative 1 from the denominator up to the numerator, x to the first. And so, limit as x approaches infinity of x to the first is just infinity, right? Which doesn't work with the whole formula. So we keep r bounded like that. But for these, they're not negative. This is n to the first. We just apply the limit directly. And we get 5 plus 0 over 1 plus 0, which is just 5. So by far, I would probably say that the most tedious one was probably the L'Hopital's rule. But if you're in a pinch, right, a lot of students kind of forget that any method other than L'Hopital's exists after figuring out the formula. That's what they usually use. Uh, so if you're ever in a pinch, you can always just fall back on that. All right. So we could do one that diverges. Right, so 25. All right, just the next one. Nothing too hard. And so the fourth over n cubed minus 2n. Right, and right off the bat, you kind of see, right, by looking at horizontal asymptote rules, that since, looking at the highest degrees, since n, where, this is x to the n over x to the m, if n is greater than m, then there is no horizontal asymptote. So there's nothing for this to converge to. This would just diverge. Right, but if you wanted to kind of show it through, using rules for sequences, showing that the limit would diverge, or that the limit doesn't exist, right? We're going to use the same strategy we would use for trying to show or trying to find the limit, right? So highest degree, right? Divide the top and bottom by that highest degree. We would get the limit as n approaches infinity of 1 over n minus 2 over n cubed, right? Which if we apply the limit, 1 over 0 minus 0, that does not exist, right? That would be 1 over 0. Or we could kind of do something similar, but use the highest degree of the denominator, right? I'm showing you all these, showing you guys all of these different ways. You probably only need to use one, but if you think that one is better fit for the situation, or if you just like to use one more, then you have all, you could just choose any one of these and be good. So here we could just apply the limit, right? We get, well, as n approaches infinity, we have infinity over 1, which is infinity, which also does not exist. Right, so a lot of ways to show that this just diverges. Right, so it all kind of leads back to, oh, it diverges, right? And I'm just showing you different ways to show that it does. Okay, this one uses a rule that I never saw in like Calc 1. Everything so far has been kind of Calc 1-esque, right? And depending on your professor, depending on your teacher, I'm sure this rule was shown in some lecture at one point, but I'm just going to rewrite this as 3 over 7 to the n. So there's a rule, right, or theorem that states that if a to the n, or rather, if the limit as n approaches infinity of a to the n, if we have a function that looks like this, then if a is, let's see, if the absolute value of a is less than 1, then the limit as n approaches infinity of a to n equals 0. So what do I mean by this? Absolute value of a is less than 1. Well, you can also write this as a is between -1 and 1, right? Not including -1 and 1. If it's any one of those, then well, -1 would diverge through oscillation, right? -1 to the nth power would jump between -1 and 1 depending on the power, right? -1 to the first is -1, -1 to the second is 1, right? So it would go between -1, 1, -1, 1. That would just diverge. But for 1, then, 1 to the nth power is just 1. So kind of an easy limit, right? It's a constant, so it just equal 1. But for any fraction, right, like, I'm not going to use this. Right? You should be able to see that it'll apply here after, but say we have 1/2 to the n power. Well, 1/2, right, if this is our sequence, then at n equals 1, this would be half. At n equals 2, this would be 1/4, 1/8, 1/16, 1 over 32. These are all getting closer and closer to 0, right? And then there's another theorem, right? So the reason why I say absolute value and why it could be like -1/2 to the n If I don't put bounds here, and by bounds I mean these guys, uh, by convention it's assumed that n starts at 1 and goes towards infinity. But there's this theorem that states that the limit as n, if the limit as n approaches infinity of the absolute value of a of n equals 0, then the limit as n approaches infinity of a sub n also equals 0, right? And we can kind of see through, say, -1/2 to the n, right? This is a great example. Um, so just a to the n, right? Let's take that. So to the first power, this would be -1/2, second power, 1/4, third power, -1/8, 1/16, -1/32, so on and so forth. These are all, right? Say this is 0. These are all getting closer and closer to 0, right? It's, on either side of it, but if you go all the way to infinity, this number would reach 0 at n equals infinity, which doesn't happen, but that's why we have limits, right? So a sub n, so we could just say that if the absolute value of a sub n of the sequence equals 0, right? That would be the same thing as the limit as n approaches infinity of just a sub n equals 0, right? Case 1, we have this. So the limit as n approaches infinity of -1/2 to the n power, that still equals limit as n approaches infinity of 1/2 to the n power. So it's a pretty neat theorem. Lets us do some stuff that we otherwise couldn't. Not useful for this case, but will be useful later. So since 3/7 is between 0 and 1, or -1 and 1, um, the limit as n approaches infinity of 3/7 to the n, it's just going to converge to 0 by that theorem. Not too bad, you just have to know a theorem. Right. Okay, 29. I thought this one was pretty interesting. So we have a sub n equals e to the -1 over square root of n. Right. And remember, for these questions, we're just asked, does it converge, does it diverge, and if it converges, what number does it converge to? So I'm going to rewrite a sub n, which is the sequence here, as 1 over e to the 1 over square root of n, right? Just using a little rule where x to the -n equals 1 over x to the n. All right, just applying this rule here. Right, and I could probably write this in as, probably write this blue or whatever, but it's okay. Just to kind of differentiate it from the problem. And we could take the limit as n approaches infinity of 1 over e to the 1 over square root of n. Oh, there's another limit rule, and this applies for like any limit. The limit as n approaches a of f of n, right? We usually call this x, right, for any function, right? But rules that apply for functions can apply to sequences as well. The limit as x approaches a of f of x equals f of the limit as x approaches a of x. So we could use that rule here. So the limit as n approaches infinity of 1 over e to the 1 over square root of n, this is going to equal 1 over e to the limit as n approaches infinity of 1 over square root of n. And recall from a rule that we used earlier that the limit as x or n approaches infinity of 1 over n to the r, where r is greater than 0, will just approach 0. So even though square root of n isn't like 1 or something nice, it's still n to the 1/2, which is 1/2 is greater than 0. So this just equals 1 over e to the 0, which equals 1 over 1, which equals 1. And e to the 0 equals 1 through a rule that states that any number to the 0th power equals 1. Right? Small little rule. Comes in, all of these rules come in handy actually. Okay. Yeah, 31 doesn't look too bad. I'm gonna go through this one a little bit quicker, just because I think at this point it's a little bit trivial compared to some of the other ones we've gone through. All right, or not necessarily, we haven't gone through any hard ones, but I would say it's trivial by like it being similar, and since it's not using any new theorems. Right, so limit as n approaches infinity of square root of 1 plus 4 n squared over 1 plus n squared. Well, we could just use the rule that we mentioned earlier. This is just limit as n approaches infinity. That's the composite rule of limits. Right. We apply that here. This is just 1 plus. Actually, I'm going to rewrite this in a way that would make it simpler to use a horizontal asymptote rule that I use on the first question. Right, and this just equals the square root of 4, right, by the horizontal asymptote rule, which is 2. So it converges to 2. Very simple. Not too bad, not too bad. I'm gonna skip 33. I'm actually gonna go to 35, right? Because these is the rule that I mentioned earlier. So recall that if the limit as n approaches infinity of a sub n, absolute value of a sub n equals 0, then the limit as n approaches infinity of a sub n also equals 0. So we could just apply this rule here. So then the absolute value of a sub n is just going to be, well, the absolute value of -1 is just going to be 1, right? Absolute value of 2 square root of n, well, that's just 2 square root of n for the sequence, since the sequence is defined as having inputs where every input is a positive integer. So then the limit as n approaches infinity of 1 over 2 square root of n, well, like I said, this is just a 1 over x to the r function. So this is just going to equal 0. Right, and I kind of use this rule kind of assuming that it's going to approach 0, which it does. So conveniently for us. So since the absolute value of a to n converges to 0, then a sub n must also converge to 0. Right, I kind of put a brilliant explanation there since the answer kind of comes from using a theorem. Okay. 37, this one's quite interesting. Or at least I thought so. So 37, we have a sequence. So I believe this is the first one we're using this sort of sequence notation of 2n minus 1 factorial over 2n plus 1 factorial. So if you've never seen this problem before, this particular problem, you'd probably be freaking out, like I was, because I haven't seen factorial in a math class yet until this point, right? Some of you probably have, but for me, this was my first time seeing it in a class at least. I've seen it before, right? Just because it's used every once in a while, but in math class, we never really talked about it. So here, I'm just going to define factorial, so n factorial, right? This is just n times n minus 1 times n minus 2 times, whoops, undo, times n minus 3, so on and so forth until we get to say 3 times 2 times 1. Right. So in the case of, say, 7 factorial, this is just 7 times 6 times 3, my bad, times 5 times 4 times 3 times 2 times 1. Right? This is a big number, right? But so I'm not gonna compute this, but we could say like we could find out 3 factorial, that's not too bad. 3 times 2 times 1, that's just 6. Right? 2 factorial, that's just 2 times 1, which is 2. Right? And so on and so forth. So in the case of 2n minus 1 factorial times 2n plus 1 factorial, right, this is just going to be 2n minus 1, right? Applying the definition of factorial, and by the way, factorial is only defined at integers, positive integers, right? So there's no 7.5 factorial, that just does not work. So it works pretty good for sequences, actually. So 2n minus 1, we start out with our, and then n minus 1. Well, 2n minus 1 minus 1. Right, that's just 2n minus 2. And then we can continue 2n minus 3. So on and so forth until we get to like 3 times 2 times 1. Right, each of these just multiplying. And all of this is going to be over 2n plus 1 times and applying the same rule. So 2n plus 1 minus 1 is just going to be 2n, which then becomes 2n minus 1, 2n minus 2, 2n minus 3, right? So on and so forth. So we get to like 3 times 2 times 1, right? And here we see something interesting happen. I'm actually going to rewrite this as 2n minus 2, and I'm actually going to color code this a little bit better. So 2n minus 1, 2n minus 2. So we can actually see something here. For every term on the top here, this is going to cancel out with every term on the bottom here. Or every factor, my bad. Right, and this is going to continue and cancel every one and leave us with these two factors in the bottom. Right, and at the top we're left with 1. So all that we're left with is 1 over 2n plus 1 minus 2n. And just by a property of how this function was set up and how 2n minus 1, 2n minus 2, 2n minus 3 is going to cancel out with everything to the right of, 2n plus 1, 2n, 2n minus 1, 2n minus 2, 2n minus 3. Everything to the right here is going to cancel out with everything to the right here onto infinity. And all we're left with is 1 over 2n plus 1 times 2n. So we could just take the limit as n approaches infinity of 1 over 2n plus 1 times 2n, right? And this is pretty easy. It's just going to be 0. Converges, right? Just using that same rule of limits at infinity that we've been using this entire homework. So that was a little bit, you probably wouldn't even know how to start if you didn't know the trick, but once you do, it's not too bad. Okay, 39. Sequence of sine of n. So here we could just, try to do it directly and pretty easily. And there's no trick here. It just diverges, right? It just oscillates. If you think of a sine function, it's a pretty wacky coordinate plane. But if you think of a sine function, that's all that it does, all the way to infinity. So if you go towards infinity, it's not going to converge, right? It just does not converge to a single number. It just goes up to 1, goes down to -1, and just cycles back and forth, and everything in between, right? For a sequence, it's a little bit hard, it's a little bit less line and more dots, but like we said earlier, we could apply it like it's an x, as if it's a f of x function. So no trick there, just doesn't converge. 41, it just uses L'Hopital's rule. So I'm not going to go over that one. It's not too tricky. Let's go over something that is a little bit trickier. Something that uses something we haven't seen before. 43. A sub n equals cosine squared of n over 2 to the nth power. Okay, so this is going to use what's called the squeeze theorem. So all of the squeeze theorem states is that for any function, for any three functions rather, say f of x, h of x, and I don't know, think of a variable here, k of x, I guess, right? The letters don't matter. It's all arbitrary, but I don't think this is what you would find in your textbook. So if f of x equals k of x, right? And this isn't really what it's used for. It's more likely they're going to use it as the limit as x approaches a of f of x equals the limit as x approaches a of k of x, right? If you have three functions set up like this, then the limit as x, if the limit of the left function equals the limit of the right function, then by definition, since it's kind of squeezed in there, the limit as x approaches a of h of x, if these equal one limit, this has to equal that limit since it's kind of squeezed in there, right? If this approaches 2 and this approaches 2, then there's no other number that this function can be. Um, as say x approaches 5 or whatever, right? So we can use that sort of logic here. So cosine squared of n. Well, let's just think of what cosine squared of n has to be in between. So normally for a cosine function, right? Um, it starts off at 1, right? And it goes down to -1, and it just, goes back and forth. So it never goes in between. So cosine of x, right? This is a f of x equals cosine of x. That's all this function is between -1 and 1. Well, if you square cosine, and cosine has to be in between -1 and 1, then cosine squared has to be in between 0 and 1, right? All these values turn positive, right? And then you get a couple of differences in the graph. So all the negative values, they turn positive when you square cosine. And for like 1/2, you get 1/4 or whatever. But these are all fractions. They're not going to go above 1. And then at 1 is still 1. Right? So a cosine squared function is always going to be in between 0 and 1. And now this is a compound inequality. We can kind of treat this like an equality and divide everything by 2 to the n. This should preserve the compound inequality. So we get 0, and then we get cosine squared of n over 2 to the n, and then we get 1 over 2 to the n. Okay. And, this should all still be true. No matter what n is, right? This will never be negative. If this was, negative, you would switch inequality signs to the other way, all that. Um, but in this case, you don't have to worry about anything like that. You just, be a little bit mindful of it when you're working with inequalities, whether you would switch it or not. So we could take the limit as n approaches infinity of each of these. And here we see why knowing the squeeze theorem helps. So the limit as n approaches infinity of a constant, that's just, that constant, right? We're going to keep the middle the same, right? Because we're not so worried about evaluating this. We've already stated, oh, we can't evaluate that. And the limit as n approaches infinity of 2 to the n. Well, not exactly our 1 over x to the r rule, but kind of using a similar logic. If you have a fixed constant on the top and you have some sort of function at the bottom with a variable in it, and this bottom function is approaching infinity, well, constant over infinity is just going to be 0. So this is going to be 0. And, well, would you look at that? By the squeeze theorem. So we can say here, by the squeeze theorem, the limit as n approaches infinity of cosine squared of n over 2 to the n equals 0. Therefore, yeah, this was defined as a to the n. So the sequence a sub n converges specifically to 0. not too bad. Right, just a little bit of the squeeze theorem, and we squeezed out an answer. Ha ha ha. Okay. Um, 45 has a bunch of different ways to do it. I think they're all pretty simple once you get through one little trick. So, since the trick isn't exactly obvious, I'll just go over it. So, for 45, so we have the sequence a sub n equals n sine of over n. Well, algebraically, n equals 1 over 1 to the n, or 1 over 1 over n, right? Because dividing by a fraction is the same thing as multiplying by its reciprocal, right? So this whole thing still equals n, right? But there's just a different way of writing it. So then we could rewrite a of n as sine of 1 over n over 1 over n. Right. Okay. So then we take the limit as n approaches infinity, right, to see if the sequence converges or diverges. Sine of 1 over n over 1 over n, right? And this actually looks very similar to something from Calc 1. So in Calc 1, we learned that the limit as theta approaches 0 of sine of theta over theta equals 1. And this uses some fancy trick from um, the squeeze theorem. I just watched Khan Academy's video on it. I thought it did a really good job of explaining how we can come to that conclusion. Anyways, um, what we could do here is say let t equal 1 over n. So as n approaches infinity, t, then t approaches 0, right? If we take the limit as n approaches infinity of 1 over n, then that's just 0. So then as n approaches infinity, t has to approach 0. So then we have something that works really well for us. So limit as t approaches 0 sine of t over t. And we know by this theorem that this has to equal 1. And this converges to 1. Right, final answer is that it converges to 1. And then I think I'm going to do the last problem for today. So if you haven't already, I would ask for a follow, right? It doesn't hurt. I don't stream very often, but when I do, it's, nicer to have some engagement. So if you're watching this at any point and you found this helpful, a follow would be appreciated. Having someone here to ask questions also helps. So since I got that out of the way, now that I've gotten that out of the way, let's get onto it. 47. So the sequence a sub n equals 1 plus 2 over n to the n. And I think this is a really challenging one, and it's a great one to leave it off. So I'm just going to go ahead and say I'm going to use a little algebraic trick, right, that you see every once in a while. That just pops up. So we can say that x equals e to the ln of x, right? And this is, wonder what that was. Thanks for the follow. All right. So there's a little algebraic trick that comes from logarithm and exponential rules that says that e to the ln of x is just equal to x. Right? And if we can, well, there's not much to it. That's just kind of by definition that e and ln are inverse functions. So if you have ln of x, right, and you apply e to it, then e and ln are inverses and you get x. Right, but we could always go the other way around. So we can use that here, right, and say that this equals e to the ln of 1 plus 2 over n to the n. And then we can use a logarithm property that states ln of u to the r power equals r ln of u. So then this equals e to the n ln of 1 plus 2 over n. Okie dokie. Now we're getting somewhere. And then we could take the limit as n approaches infinity of this function to figure out if it converges or diverges. Right? And then using a property of composite functions, a limit of composite function rule, we say that this equals e to the limit as n approaches infinity of n ln of 1 plus 2 over n. Right. So this, if we just apply the limit directly, we would get, let me undo that, do it in a different color. We would get infinity, and then 2 over n, if we apply the limit here, this is just 0, which is just ln of 0, which is 0. So we get 0 times infinity. This is a indeterminate form where we can apply L'Hopital's rule. The only thing here is that we would have to transform it into a 0 over 0 form and then apply L'Hopital's rule. So we could say that this is e to the limit as n approaches infinity of ln of 1 plus 2 over n, and as stated before, n equals 1 over n. This is algebraically equivalent, right? This is 1, divided by a fraction, same thing as multiplying by its reciprocal, right? This just equals n, right? So that checks out. So then we could apply L'Hopital's rule, right? Because this is 0 over 0. Right, so derive the top, we'd get, so 2n to the negative first, this is negative 2 over n squared, right? 2n to the negative second. So deriving ln of this is just 1, sorry, not 1, negative 2 over n squared divided by, right? Deriving an ln function is just u prime over u, right? Deriving ln of u, equals u prime over u. Right, so this is all over 1 plus 2 over n. And then derive the denominator, we get negative 1 over n squared. Oh boy. Keep in mind this is all in the numerator of e. So this is e to the limit as n approaches infinity. Let's clean this up a little. Negative 2 over n squared divided by 1 plus 2 over n is the same thing as multiplying by 1 over 1 plus 2 over n, right? And dividing by 1 over divided by negative 1 over n squared is the same thing as multiplying by negative n squared. And we can see here the negatives are going to cancel out and the n squareds are going to cancel out. And now this limit kind of falls into place. Limit as n approaches infinity of 2 over 1 plus 2 over n. Right? So if we apply a limit directly, 2 over 1 plus 0 equals to the 2 over 1 equals squared. So this converges. Beautiful problem. I thought it was really fun. Right, I thought it diverged at first, honestly. I wasn't even really sure what to do there. But like I had to look at the answer key. But once I saw that E was in there, I kind of put two and two together that I had to do some algebraic trickery to get this into a form that we could apply the limit towards. So, for anyone who decided to hop in and is listening to this right now, I want to thank you for your time. I hope that this was helpful. If you found it helpful, please, consider following and maybe tuning in next time. And you know, come with questions. I don't mind helping on something that we're not even covering, right? I just chose chapter 11.1 because that's what I was doing right now. But if you guys want, we can do any level below, right? As long as it's within my capabilities, I don't mind. We can do Calc 1. We could do something from an earlier chapter, uh, algebra, even if you guys want. I just want to help. So if you guys have anything that needs help, I'm here. I hope you guys enjoyed, got something out of it, and I hope to see you guys here next time. Bye.